Hello, and I would like to perform a derivation video. That is to derive the kinematic relationships for rotation. There are kinematic equations for constant acceleration for linear, that is for one-dimensional variables, but I would like to use calculus to also derive how rotation should be true for kinematics as well. So let's go ahead and have a look at this circle. And let's imagine that some portion of the circle, you could imagine as the entire solid body or just a particle from this point that we imagine to this point out here, rotates through some angle of interest. Okay? So if we rotate through this angle, let's go ahead and call that delta theta, some angle change. And it turns out we should derive what that angle change is in terms of delta theta. And here's how we can derive it. So we know that an angle change, delta theta, should equal to a distance along a curved arc divided by a radius. So let's call this distance radius r, here to here, and the radius is constant for this circle. And then this curved distance along the outer edge, we'll call that s. So s is the curved, we might call it arc length, or curved distance along the outer edge. So what we can say is we can say that delta theta will be s divided by r. Now what units will that have? So that'll be units of meters divided by meters. So in some sense delta theta ends up being unitless. So given that delta theta is unitless, we should give it a name. Now here's how the name is often presented. For a full circle, we know that s, the arc length, is exactly equal to the circumference. That's the distance all the way around the circle. And that distance we know to be the well-known geometry formula, 2 times pi times r. That is 2 times the special number pi times the radius. And we divide by radius. So we cancel these out and we say that for a full circle, and I should have written this not as s, but so for a full circle, s would be 2 pi r, but if we do s divided by r, that would be circumference divided by r, there we go, and that should be delta theta. So then delta theta equals 2 pi for a full circle. Or we often call that a full revolution. So one full rotation or one full revolution is 2 pi. And this we call the units of radians. So radians is actually going to be the SI unit, but it's also basically unitless. And that's because one full rotation in terms of an angle all the way around here is really zero displacement. So radians are a good counting unit, but they don't count for an actual physical dimension per se. Okay, so this leads us to an important equation. Notice that delta theta is going to equal to delta theta times r is going to equal to s. So we can say s is equal to delta theta times r. Okay, so we'll keep that equation over here. And in fact, I'll label this equation with 2 other equations that are very similar afterwards. Okay, so this is how we relate linear quantities of radius and arc length, s, to angular quantities, namely delta theta in radians. So again, I should write that down. S we call the arc length. Okay, this, by the way, is the center of the circle. That is the axis of rotation. Now let's see what happens if we start introducing how fast of a rate of rotation. So that we would call a velocity. So here, let's imagine that this object is rotating at a certain rate. So this right here is going to be the rate of rotation, and that rate of rotation, we'll give that a name. We'll call that omega. So this is going to be the Greek letter omega, and we'll call that the angular, sometimes called the rotational velocity. That's how fast the object is rotating, maybe as a solid body. This entire turntable, let's say, is rotating as a solid body. So by definition then, omega average should just be the change in theta over the change in time. Okay? So it's the change in the angle over the change in time. Now, if you want the instantaneous rate of change, you should bring in the calculus. So I'll change that to calculus. So we should let delta t approach 0 in the limit. And that should be omega is just d theta dt. And this is what we call the angular velocity. That's how fast theta is changing in time. So notice that if theta changes, but it also changes with time, that's going to give the omega. Also note that omega is related to a linear quantity. Notice that you could imagine that on the outside, an object is going to be moving at a certain linear velocity. So the linear velocity like so. And that linear velocity is going to be tangent to the circle and perpendicular to the radius. So we could say the linear or the tangential velocity on the outer edge should still have units of meters per second. And if we call that v, vt, v tangential, then we can get a relationship between omega and v tangential. In fact, in order to get that relationship, we just take the time derivative of this equation, assuming the radius is constant. So if s is equal to delta theta times r, we know the time derivative of theta with respect to time should be omega. So this should be omega times r, and that's equal to the tangential velocity. By the way, what is the units of omega? Omega should have units of radians per second. Because again, theta is in radians, time is in seconds. Notice radians per second, so let me write this out. Radians per second times meters for the radius should give meters per second for the linear or the tangential velocity. Lastly, what about if this object is accelerating? If it's accelerating. Well, let's switch to an even different color. So if this object is accelerating, then the idea is that not only is it accelerating, we should give that a name. So it's accelerating the rotation rate. Let's give that a letter, and let's call that alpha. So now this is the Greek letter alpha. So again, alpha. And let's give that a name. That's going to be called either the angular or the rotational acceleration. So alpha, by analogy to these other definitions, alpha is going to have units of radians per second squared. Why is that? Because alpha average should be change in omega over change in t. That's the change in the angular velocity over change in time. And by the way, in fact, if there is an acceleration, you can imagine that the velocity is actually getting larger. So that means this velocity is getting large, a little bit larger here, but then here it's getting still tangential, but it's even larger. Okay? So that's kind of the idea as time goes along. And then we could also say that if we use calculus, that alpha should just be the time derivative, that is d omega dt, the time derivative of the angular velocity. Now, one more thing, you may ask, how can you get the tangential acceleration? So that would be the acceleration along the tangent edge. You might call this the linear acceleration. So this is at. Well, the tangential acceleration, by analogy, should be the time derivative of the linear velocity equation. Assuming constant radius, the angular velocity time derivative should be the angular acceleration. So it should be angular acceleration times radius. So we sometimes call these equations the linear to rotation equivalencies for rotation. Okay, so there they are. And notice what we have is we have a couple definitions here. We have this important definition up here for how the angular displacement is related to the arc length and the radius. We have the definition of circumference, c equals 2 pi r. We have the definition of radians, that 2 pi radians is 1 revolution. We have the definition of angular velocity as the change in angle over change in time. We have the definition of angular acceleration as the change in angular velocity over change in time. We have these linear to rotational equivalencies. And let's see, anything else? Now you may also ask, how long does it take? What's the time period for one rotation? So the time for a rotation is equal to capital T, and that we call the period. And that should have units of seconds. Now for the period, I'll just write it up here. The period can be written in a couple ways. If you do it in terms of rotation, you can think about that an entire rotation is 2 pi radians. And the rate of rotation, if it's constant angular velocity, is going to be omega. So this would be 2 pi divided by omega as long as omega is constant. Now, the period is also going to be, as long as v is constant, as long as the velocity is constant, if you want to figure out how far to go along the outside tangent edge, so in other words, in terms of linear, you could write the circumference divided by the linear velocity, because that's like distance divided by velocity. So this is 2 pi r over vt. And vt is the tangential velocity. Okay, so that'll give you the period. So period can be calculated in several different ways. So these are all, and let me box these equations because these are important as well. So these are all the important rotational kinematic equations that you should be aware of. Okay, so thank you very much. Hopefully this derivation from scratch was helpful because you can see where these equations and concepts come from. So please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social network, and please let us continue to have good discussion through the comments. Thank you for your attention, and thank you for watching High Peak Education. I will see you in the next video.